You're welcome to day 38 of 50 days of tutelage. In today's class, I'll be talking about heat transfer. So basically, I'll be discussing on the modes of heat transfer. I'll also be talking about quantity of heat transfer. This will involve some calculation that has to do with specific heat capacity and all of that. So let's talk about mode of heat transfer first. We have three major ones, and these three major modes of heat transfers, they also kind of involve different state of matter. For example, the first one, which is known as conduction. Conduction. This only involves solids. This happens in solids. And what is this conduction process? What is it like? So let's say, for instance, you have a solid part, a solid substance here, and from what you know about the particles of a solid, they are always closely packed together. So permit me to just roughly put them here. So these are the particles of the solid. This is just a rough depiction. So when you supply it from one place, so let's say you're supplying it from this end, what happens is that the average position of these particles remains the same. They are not switching places. This is not taking the place of this. This is not taking the place of this. This is not taking the place of this. The average position of the particles will still remain the same. But it is going to gradually transfer itself. It's going to gradually transfer itself from this end to this place. So it's moving, it's transferring rather, and it is spreading. So when you supply it to one end, it is properly transferred and taken to the other end without anybody actually moving. The only thing that they do is that these particles vibrate about their main position. They vibrate about their main position. So transfer of heat such that the average position of the particles of that body remains unchanged is called conduction. Which is why if you want to transfer it from one body to another, from body 1 to body 2, unfortunately, you cannot transfer it between these two guys through conduction unless they are in contact or there is something that is connecting them together. There must be some way they are connected, whether you are connecting them directly or you're connecting them with a conductor. That is the only way you can transfer it through conduction between two bodies. Now, let's go to the next one. The next one is convection. So, convection rather. So heat transferred due to convection. Now, how does this work? The first thing you need to know is that this only takes place in fluids. This only takes place with fluids. So fluids, it can be liquid and it can be a gas. It can be a gas. It is quite the opposite of conduction because it is transferred by the actual movement. It is transferred by the actual movement of the particles of these substances. For instance, if you're boiling water, this is what happens when you're boiling water. So you have water in a container, then you supply it to this container. So what happens? All the substance, all the water substance at the bottom of the container, which are closer to the heat source, they get heated up. I'm going to explain what is going on here in two different ways. The first thing that happens is that when you heat up this amount of water, when they get to a certain temperature, any temperature that is above 4 degrees Celsius, what happens to them is that they expand. So due to this expansion, if you go back to the previous class, I'd already explained to you about flotation. So due to this expansion, their density falls. The density of those water at the bottom, it falls. And from what you know, the less dense guys always stay at the top. When you are less dense, you float. You don't stay at the bottom. So because of this lesser density now, due to expansion in their volume, then these guys will move up and they will be replaced by the immediate level of water above them. So this is going to happen to those immediate level as well. They will also move up. And this continues to happen when the one at the top, they are not as hot as they were before, so that the one at the bottom, they are now hotter now. Then they also go down again. So this is what happens repeatedly when you're trying to boil water. And after you have been able to reach a certain time, then this happens more spontaneously. That's the first way you can see it. Another way you can also see is that when it is supplied from this bottom here, The particles down here, because energy is transferred in form of heat, but the particles here will gain what we call kinetic energy due to the heat that you have supplied to them. And because of that kinetic energy that they have gained, what happened to them is that they move up, they are excited upward, and the immediate water above them, immediate water particles above them, will fall down to the place closer to the heat source, and they experience this as well, and they go on and on like that until convection current is set up. So convection is the mode of transfer of heat such that the particle of that fluid or the particle of a fluid, they are actually the carrier of this heat itself. So this, if there is or a gas a liquid or a gas in a room or in a certain system, the through convection, heat can be carried by such from one point to another. So remember body B1 and body B2. If body B1 is hot and body B2 is feeling the heat of body B1 without them touching each other, then most likely what is carrying is the air particle in that room. So the air molecule in that room is the one carrying the heat from body B1 to body B2, and it's doing so through the means of convection. Convection is the means. The last one is radiation. The last one is radiation. So what is radiation? Radiation is not necessarily similar to convection, but it also involves that the two bodies are not in contact. There's a transfer of it from body B1 to body B2, and they're not in contact. But if you look at this one now, the air molecule, the air particle that surrounds them has to be heated up before this B2 will feel the heat. So the transfer is actually because the air molecule is the one transferring the heat. But in the case of radiation, there is going to be a transfer of heat from this place to this place. So there is heat here, and heat is just suddenly transferred to this place without necessarily involving the intervening medium. Without necessarily involving the intervening medium. So you can see that it doesn't have to use the air molecule or water molecule or whatever molecule that is between them. It doesn't have to do that. Heat is just transferred directly from one body to another. And that is the way the heat from the sun actually reaches us on Earth. It reaches us through radiation. It reaches us through radiation. So please take note of that. You need to also take note that the best radiators of heat are always dull. Yes, dull surfaces, rough surfaces. These surfaces are best radiator of it. But the moment you have a polished, shiny, polished, smooth surface, these are poor radiator of it. They reflect it way too much than actually hold the heat to themselves. So good radiator of heat, rough and dull surfaces. That is why wearing a black cloth in the sun, you attract more heat to yourself and you feel the heat more than wearing a white cloth. So that's that for mode of transfer of heat. Let's talk about the quantity of heat now. So for quantity of heat, I'll be talking about the specific heat, then I'll be talking about the latent heat as well. So I'll be discussing about the specific heat and the latent heat. So let's talk about the specific heat first. See, there's a certain heat that changes the temperature of a body. So if you have an initial temperature theta I, then if heat is supplied to you and the heat changes your temperature to a new temperature, let's call it theta F, then this heat has to do with specific heat. And it varies in so many ways. If the if we take just 1 kilogram of a body and we supply a particular amount of heat to that 1 kilogram of a body, and it changes the temperature of this body by 1 degree Celsius or by 1 Kelvin. By the way, a temperature change of 1 degree Celsius is the same thing as a temperature change of 1 Kelvin. They are the same change. So if you supply heat to this body, 1 kilogram of a body, or we say a unit mass, and it raises the temperature of that body by 1 degree Celsius or 1 Kelvin, then what we just did was to supply it the quantity of heat that is equal to its specific heat capacity. So specific heat capacity of a body, denoted as C, is the quantity of heat that is required to raise the temperature of a unit mass of that body by 1 degree Celsius or 1 Kelvin. So that is what specific heat is, a specific heat capacity. But if you are discussing about heat capacity itself, heat capacity is the quantity of heat required to raise the temperature of the entire body, to raise the temperature of the entire body by the same 1 degree Celsius or 1 Kelvin. So we have specific heat capacity and we have heat capacity. So for heat capacity is the quantity of heat required to reach the temperature of a unit mass. So if it's a unit mass, then we divide it by the entire mass, and then we divide it by the change in temperature, because we only want to raise it by what? By 1 degree Celsius or 1 Kelvin. So this now implies that the quantity of heat is now m multiplied by c multiplied by change in theta. So where m is the total mass of the body and c is the specific heat capacity, and change in theta is the change in temperature caused during this heat transfer. So therefore, since I've defined heat capacity as well, let me denote heat capacity itself. Let me denote it with Cp. So this is specific heat capacity. Why is it specific? I'm only raising the temperature of 1 unit of the body, and which is why for every substance they will always have the same specific heat capacity as long as they are made of the same material. So if you have, let's say, copper now, copper we always have the same specific heat capacity no matter how big. So if this is a chunk of copper, if this is also a chunk of copper, both of them will have the same specific heat capacity. But in the case of heat capacity, like I said, it is the quantity of heat required to raise the temperature of the entire body by 1 degree Celsius or by 1 Kelvin. And this is actually given as MC. The heat capacity of a body is given by what? Is given by MC. Is given by MC. So therefore, the heat capacity of a body, it can change from one value to another because it depends solely on the mass of that body. It depends solely on the mass of that body. Like I said, um, specific heat capacity is the heat required to raise the temperature of a unit mass of a body by 1 degree Celsius or 1 Kelvin. For heat capacity, it is the same process, just that this time around, it is the one required to raise the temperature of the entire body by what? By 1 Kelvin. The entire body by 1 Kelvin. So majorly the difference here is that in this place, instead of you dividing by m and changing theta, you only divide by what? You only divide by m in this situation, and so you get your result like that. So let's proceed. How do we use this thing in calculation? You need to be able to determine that which body is losing heat. So one body must lose heat and one body must be the one gaining it. Know that anybody with the higher temperature, if you are the one with the higher temperature, you will be the one that will lose it. And if you are the one with the lower temperature, you are the one that will gain it. So it always transfer from the region of higher concentration to a region of lower concentration. So if this has a particular temperature, so let's call this T hot, hot temperature, and let's call this one cold temperature. When we say cold now, it doesn't mean that it's actually cold though, it's just the colder one. So I think I should just use figures. So let's use theta 1 for this and let's use theta 2. So and let me denote that this is the hot body. So this is the outer body, the outer body. So if you want to do the whole change in whatever, now know that the quantity of heat that this one is losing is the quantity of heat that this particular guy is gaining. By the way, it doesn't mean that the quantity of heat of this is way more than the quantity of heat of this. The only difference here is that this one has a higher temperature than this other one. This one has a higher temperature than this other one. That's the major thing that is the difference between the two of them. So what you do is that you say M1 C1 times change in theta will be equal to M2 C2 times change in theta. But here's the thing, when this continues to happen and this guy begins to lose heat to the body B2, there is a particular point where they will reach, which we call thermal equilibrium. Both of them will have a steady temperature, which will be the same. Once that has happened, there's no longer transfer of heat. Even if one tries to transfer, the other one will transfer back, and they will maintain that steady state temperature. So the change in temperature for this, how we find the change in temperature for somebody who is losing heat is different from how we find the change in temperature for somebody who is gaining heat. So in this case, change in temperature for the first person will be their initial temperature minus the steady state temperature. But for the person that is gaining the heat, so their change in temperature will be the final steady temperature minus their initial temperature. So take note of that. But if you have, let's say, more than two bodies, if you have like three bodies, how can you always do this? So you can just say that summation MI change in theta I equals 0, because summation of all the form of heat transfer will always be equal to 0. And how do we do this? So let's say, for instance, you have body B1, you have body B2, and you have body B3. So each of them at a temperature of theta 1, theta 2, theta 3 before the whole transfer is happening. And all of them attain a steady temperature of theta S. So all you just have to do is that just say M1 multiplied by C1, then multiplied by the change in temperature will be the steady state temperature minus initial temperature. You have M2 C2, the steady temperature minus the initial temperature. Then you have M3 C3, the steady state temperature minus the initial temperature. Everything will be equal to 0. So what I've done here is that I'm not doing all this gimmick of, oh, which one is losing, which one is gaining. I'm just assuming that I don't know which one is losing, I don't know which one is gaining. But I know that the steady state temperature is theta S, so I will subtract all the initial from this final. But this time around, I'm not putting them on different sides. I'm adding all of them together, and they will definitely be equal to 0, because that's exactly the way it works. So you can always use this when you have more than two bodies involved, and this will always help you get the proper result that you need. So this is for specific heat capacity. What about latent heat? We have another one called the latent heat as well. Latent heat. This latent heat, in this case, it causes a body to change their state, but they do not change temperature. So change of states usually happen, that is from solid to liquid to vapor. But change in temperature does not happen in this case. So it's the kind of heat that is doing some things in his body, in a system, and you probably will not notice unless you notice the change of state, unless you observe the change of state. And this is given as ml. H is the quantity of heat, m is the mass, and L is called specific latent heat. Specific latent heat. Based on what it's doing, it can be specific latent heat of fusion, or it can be specific latent heat of vaporization. So take note of this very well. If you have, like, let's say, a block of ice at some temperature, let's say negative 15 degrees Celsius, you can easily convert this thing to water at a certain temperature. So the first thing you need to do is that you need to convert the ice from negative 15 degrees Celsius to 0 degrees Celsius, because 0 degrees Celsius is the borderline temperature between ice and water. Then after that 0 degrees Celsius of ice now, so this is still ice, then you convert it to 0 degrees Celsius of water. 0 degrees Celsius of water. Then you can now raise this water to a temperature of your choice. Let's say an arbitrary temperature theta. So this is water now. So what you have noticed here is that in this situation, you have changed temperature. So what will be involved here will be the specific heat capacity. But in this case, you have only changed state, you have not changed temperature. So what will be involved here is latent heat. And then for this one, you are also changing temperature. So what will be involved here is the specific heat capacity. So basically, that's how we do calculations like that. So one bonus thing before I actually leave, I want to talk about the thermal flask. Please, you will not mind my drawing. You will not mind my drawing. So it looks something of this nature. So you have this, you have this, you have this. And that's it for today. And that's it for today. I'll see you in the next one.